Hello, today we're going to go through a sample PESE question. So you might find such a question in your exam, and we're going to take you through the working procedure and how to finally arrive at the answer. So feel free to pause the video and do the question by yourself, and then check the answer. If you cannot or if you don't understand how to solve the question, then please uh, follow the procedures and the steps we're going to take you through. So the question you're given is you are told to choose the lightest member or the lightest section to satisfy the maximum deflection criteria of L over 240, and the following information has been given: the modulus of elasticity, the maximum beam depth, and the uniform load includes the self weight. And this is the loading condition. You have a uniform load of 1 kip per foot and two concentrated loads of 30 kips each. And you're only told to choose from these four shapes: W14 by 22, W14 by 30, W14 by 34, W14 by 90. So the first step when you get such a question is to separate the loads. Okay, so you have to calculate the deflection of this structure and then compare it to the deflection criteria. So make sure it doesn't exceed the criteria that you have been given. So the first thing you need to do is to apply the principle of superposition and separate the loads. Work with uniform loads, get the deflection, then work with concentrated loads, get the deflection, add together, and then make sure they don't exceed the deflection criteria. So the first step, make sure your units are consistent, and so here we are working with kips and inches only. So from any design aid or your structural analysis books, you'll find that the maximum deflection of a uniform load is as given below. So if you plug in the values, you get the maximum deflection of the uniform load as the value in yellow. Okay, so that's the first step: get the maximum deflection due to the uniform load. The next step is the same procedure, but now use concentrated loads of 30 kips each. If you check any design aid, be it or your structural analysis books, you'll find that the maximum deflection due to a concentrated load is as given below. Okay, so if you plug in the values, you get this as the maximum deflection due to the concentrated loads. So then the third step is to just add those values together. Okay, the maximum deflection due to uniform load and maximum deflection due to concentrated load, and then you get the value in yellow. So the only unknown value that we have is the moment of inertia I. So the fourth step is now using the deflection criteria that we have been given. So you are told that the maximum deflection should not exceed L over 240, and L in our case was 180 inches. So in short, the maximum deflection of that structure should be less than 0.75 inches. With this formula, the last formula, you can actually solve for the moment of inertia, which is 337.89 inches raised to power 4. And this is the required moment of inertia. The fifth step is now to use your design manual, the AISC steel construction manual, to find the moment of inertia of all the four shapes that you were given. And if you go to table 3-3, you'll find the moment of inertia of W14 by 90, W14 by 34, W14 by 30, and W14 by 22. So since these values are you cannot clearly see the values, I have put them in the table in the next slide. You'll see that W14 by 22 is 199, W14 by 30 is 291, W14 by 34 is 340, and W14 by 90 is 999. So something you have to understand is W14 is a beam depth, and this value here, 90, 34, 30, and 22, these are the weight of the beam sections. So this is the lightest and this is the heaviest. Okay, so from our deflection criteria, first of all, you check if the beam sections actually satisfy the moment of inertia. We see that the last two, W14 by 34 and W14 by 90, are the only beam sections that satisfy the moment of inertia that we calculated. And then you go further and check which is the lightest member of the two. And the lightest is, of course, W14 by 34, and that's the best shape for this problem. That's it. If you have any question, please let me know. And yeah, good luck.